All right, we're going to go ahead and take a look at inverse functions today. We're going to look at inverse trig functions and polynomial, radical, all the good stuff, rational. And with that, we're going to be able to quickly find the derivative of inverse functions without having to actually invert the function. So if we're given an f of x and we want to find the derivative of its inverse, we're actually going to have a nice little rule that we can know that will help us find that. But just like anything else in calculus, it's not about memorizing rules. It's about understanding what's actually going on and how things kind of interconnect. So what we have here is f of x equal to x squared plus 1. You don't need to write this down. I have guided notes for you today that you're going to fill in as we go. This is just the discovery activity that we would have done had we been together for this lesson. And so I have that f of x function graphed over on the left. And I have that domain restricted to be x greater than or equal to 0 because I want this function to be invertible, which means it needs to be 1 to 1 because it has to pass both the horizontal and vertical line test. And just as a reminder, there's a couple of things we remember with inverse functions. The main role of an inverse function is to undo the operations of that function or to undo that function. So if you'll remember when we had those inverse functions and we took the composite of them, so we did like f of f inverse of x, it always got us back to just x because that's what's happening with an inverse function. What we see with an inverse function is we see that it's reflective over the line y equals x. We see that our x and our y values are switching. And so that's observationally what's going on and what tends to kind of stick in our head the most. But I want you to remember that what it's really doing is undoing. That's the whole purpose of an inverse, is to undo what's already been happening. So if I take a look at this function, first we're going to go ahead and find f inverse algebraically, and then we'll look at that graphically and see how it maps. So if I take my function, we are turning our f of x into an x and our x into a y. I'm subtracting 1. And then I'm getting y by itself by taking the square root. You'll notice that we get y equal to plus or minus the square root of x subtract 1. But since we restricted our domain to be all the positive values greater than 0 or equal to 0 in this case, what we need to do here is have our range be all the values greater than or equal to 0. And so our f inverse of x is only going to be this positive version. So I'm going to go ahead and graph this function. If I put 1 in, I get 0. If I put 2 in, I get 1. If I put 3 in, I get a radical, right? I get the square root of 2. I don't want to do that. 4, I get the square root of 3. If I put 5 in, I get the square root of 4, which is 2. And I'm going to look over here. Notice that I'm currently getting all of these outputs. I'm getting 1 or 2 I was able to put in. I was able to put in 5. I'm going to try putting in 10. I think that's going to be my next best bet. If I put in 10, I get 3 out. And let's take a look at all these ordered pairs. We have 10, 3. We have 5, 2. We have 2, 1. And we have 1, 0. And so what we do is we call these partner points. So we have 3, 10, and we have 10, 3. So those ones are partner points because they're they're mapping to different values, but they're really connected as inverse functions, right? That's the point that's flip-flopped. That's the point that would be reflected over that line y equals x. The point 3, 10 would map to the point 10, 3 with that reflection. And that's what we really want to remember, is that for every function of f(x), it has a partner point within the function f inverse of x, where that x and y values are switching because you're undoing what you've already done. So what we're going to take a look at now is we're going to go ahead and we're going to find the derivative of f of x and the derivative of inverse x, and we're going to look at what those derivatives are and maybe what a relationship might be that exists. So let's go ahead and take a look at, so we have f of x equal to x squared plus 1, and we have f inverse of x equal to the square root of x subtract 1. So the derivative of this function, f prime of x, is just going to be 2x. If I evaluate that at that highlighted point, we're going to go with 310. So if I evaluate that at 3, I get 6. I'm going to do the same thing here. I'm now going to go ahead and take the derivative of this function, which we can write in a couple of different ways. I'm going to use this notation this time, d dx of f inverse of x. We get 1 over 2 square root x subtract 1. And now if I evaluate this derivative at its partner point, so I'm not going to evaluate it at 3 because I don't have the input of 3. That's not the one that's related. My input now is 10, and my output would be 3 for the f of inverse x function. So I'm going to evaluate this at 10. I get 1 over 2 square root, which gives me 1 over 6. So notice here that if I look at their partner points, I'm looking at the point 310 here, and the point that correlates to that on the inverse function would be the point 10 comma 3. They are reciprocals of each other. So the derivative at 310 is 6. The derivative at the inverse function at its input of 10 is 1/6. Let's see if that happens anywhere else. Let's find f prime at 1. F prime at 1 is 2. That's the ordered pair 1 comma 2, right? For my inverse function, my x value, my input would actually be 2. So I'm going to find d dx f inverse at 2. That's going to be 1 over 2 times the square root of 2 minus 1, which also gives me now 1/2. So again, we have this relationship where it appears that if I know what the slope, or if I know what the instantaneous rate of change at a given x value is for my f of x function, it's going to be the reciprocal, or the derivative of my inverse function at the partner point is going to be the reciprocal of that slope. All right, so let's go ahead and take a look now at this set of notes. So we have a couple of little things that you can read through, but just to summarize, if f is continuous on its domain, then f inverse is also going to be continuous on its domain. If it's differentiable, for everywhere except for f prime of c equal to 0, it'll be differentiable. The inverse function will also be differentiable. The problem with this f prime of c being equal to 0 is that when we invert that, it's going to go from a horizontal tangent line to a vertical tangent line. And we know that a function is not differentiable at a vertical tangent line. So that's one of the reasons we had to kind of restrict this domain right here, because where we would have had a horizontal tangent line would be at the vertex right here, right, of this parabola. But by restricting the domain, we got rid of that horizontal tangent line, which resulted in a function that was fully differentiable across its entire domain. And then a monotonic function is a function that's always increasing or always decreasing. We had that function that we were just looking at, right? Half of that parabola is a monotonic function because it's always increasing for what we had. Same as the square root function. It's either always increasing or always decreasing. And those functions will always be differentiable and invertible because they don't have any horizontal tangent lines, because you're never changing from increasing to decreasing. So that's helpful. So here's our big rule, and I'm going to have you just kind of circle or highlight one spot. We're letting g of x be our inverse function, and f of x be our original function. So what this is saying is that if I want to find the derivative of g of x, again, which is my inverse function, I'm just going to do 1 over f prime of whatever the output was for my function. So it's going to be g prime of x is going to equal to 1 divided by f prime of g of x. And so let's take a look at that so that we can see what that looks like, because our output for our inverse function is our input for our original function. So that's that kind of weird part that we have to think about. So let's take a look. And these other two are just different ways. So these guys right here are just other ways that we can write taking the derivative of an inverse function. It's a little bit funky looking, so I wanted to include those in there for you. So let's use a table first, because sometimes it makes a little bit more sense with a table, and then we will look at it algebraically to try to make sense of it that way as well. And we'll do some practice problems. You'll have some on your homework, and then we'll look at it again during our review. So here's what's going on. We're finding the derivative of the inverse function at -4. So the first thing that I like to do with these so that I keep everything straight is I like to make a little table. I have my x values, I have my y, and I have two functions that I really need to look at here, f of x and f inverse of x. And what I'm trying to do is kind of make sense of what goes where. So if I have something written like that, this is saying f in the inverse of f of x, which means this is an x value. And so my x value for my inverse function is -4, which means my y value for f of x is -4. Notice that in this table, I don't have any inverse functions, right? Everything's in terms of f and g. G is not related to this at all. Just because there's a g of x here does not mean that g of x is always the inverse function. Nothing says that g of x is the inverse function. So I can't assume that. So I can only use for this problem these two columns. All right. So what I know now is that for f of x, I know the output is -4. So I'm going to go to f of x column and I'm going to find my output of -4. I know when my output's -4, my input is 0. So I'm going to go ahead and put a 0 here and a 0 there. Those are those partner points. They're related to each other. All right, so now what my rule says is that this derivative of my inverse function at -4, oopsie, sorry about that, is going to be equal to the reciprocal, so 1 over the derivative of my original function at its x value, which happens to be the output. Oops, sorry, I wrote x and not 0. Oh, we'll write it over here. So in this case, it'll be f prime of 0. So notice these two values don't match because the x value for my inverse function is not the same x value for my original function. And so for here, we'll have 1 over f prime of 0 is going to be -1. So we get -1 as our slope of our inverse function. All right, let's take a look at another one. It says write the equation of the tangent at g prime of x when x equals 1. So we're finding the derivative of the inverse function at 1. That's going to be equal to 1 over g of x at whatever, g prime of x, sorry, at whatever the output is for this inverse function. So I'm going to make my little table. I have x, I have y, I have g of x, and I have inverse of g of x. All right, it's telling me my x value, my input for my inverse function is 1, which means that's the output for my original function. So I'm going to go to g, and I see that right here is where my g of x function equals 1, which means the input for that must be 3. So now I'm going to go ahead and I'm going to evaluate g prime at 3. G prime at 3 is -2. So we have 1 over -2, which equals a -1/2. All right, let's take a look at this algebraically. For some of us, we're good. It's clicking. You're just kind of bouncing back and forth between the inverse and the original function. But for some of us, it'll be really helpful to look at this as an algebraic function. So let's take a look at this guy. We have f of x equals x plus 3 divided by x plus 1. We're looking at x values all greater than -1. Again, this keeps my function so that it's invertible. First of all, I don't have x equal to -1 would be a spot where my function is not differentiable because I have a vertical asymptote right there. Additionally, if I had any values that were less than -1, I would have that other part of the rational function, which wouldn't allow my function to be invertible. So I would have some issues. So we're just looking at one part of that function. And now what we're going to do is we are going to start off by finding the derivative of our f of x function. So f prime of x, this is good practice for my quotient rule. I'm going to get 1 multiplied by x plus 3, subtract 1 times x plus 1, all over x plus 1 all squared. So I end up with 2 over x plus 1 all squared as the derivative. Okay, so my first step is to find f prime of x. My next step is going to be to determine partner points. So I'm going to make a table here. Again, I have x, I have y, I have my f of x function, and I have my f inverse of x. And so what I need to find, it wants me to find my inverse function when x equals 2. So I'm going to go ahead and I'm finding my inverse function when x equals 2. So that means my x value for my inverse function is 2, which means that's the output for my f of x function. So now what I'm going to do is I'm going to come over here and I'm going to determine the x value when f of x equals 2. Because if my input for my inverse function is 2, that means my output for my original function is 2. So I'm going to say 2 equals x plus 3 over x plus 1. We multiply by x plus 1. We subtract x and subtract 2. We get x equals 1. So that means that this is 1 and this is 1. So now my last step, which I'm going to do over here, is I'm going to go ahead, well actually 2 last steps, but I'm going to find f prime of 1, because that's my value that I want to evaluate my derivative at. So f prime of 1 equals 2 over 1 plus 1 all squared, which is 2 over 4, which is 1/2. And now I can use that rule that we had above to determine the inverse, the derivative of the inverse function. So that inverse, or the derivative of that inverse at 2 is going to be equal to the reciprocal of f prime at 1. So it's going to be 1 over 1/2, which just equals 2. All right, so just to kind of recap, found my derivative so that I had it ready to go. I don't know the x value yet. The only thing I do know is that the output for my original function f of x is going to be 2. And I know that because the input for my inverse function is 2. Remember, your x and your y do a little flip-flop. And so I need to find what that input value is. And the way that I find that input is by letting f of x equal 2, because I know my output is 2, so I can let my output equal 2 to find what my input is, or my x value. I found x equals 1, so once I knew that, I could find f prime at 1, and then I could evaluate the inverse function. I intentionally chose a function that was pretty easy to work with. However, as you saw with the tables, you wouldn't be able to just find the inverse of f of x and then evaluate the derivative. But that could be another path for you. So like if you have a pretty easy function to find the inverse for, you could also find the inverse, take the derivative, and evaluate it at the point. The only problem is that's not always going to be an easy function to be invertible. It could be a conic. It could be a function that's like x to the fifth, something that's just very involved, that won't always be easy to invert. So we also need to have this way of finding the derivative of the inverse function for those cases where you can't easily invert the original function. All right, so you'll have lots of practice on that for your homework tonight. And again, I posted both the homework assignment and the key so that you can kind of check as you go. Once you get into the rhythm with these, it's like smooth sailing. It's just kind of reformatting your brain to think through it at first.